Wah! Mission is a go. Come on, let's try it again. Mission is a go. Howdy, everybody. We are here to do stuff and things. This evening, we're getting ourselves further to the outer reaches of space. I think I turned that down a little too much. Want a little background music onto the track end. Nope. It's finicky. There we go. That's better. Excellent. Yeah. So tonight we're gonna continue in the tirade known as the 30 Days Lost in Space. I also have sound alerts now. I have that configured. Hopefully it works. As a matter of fact, let me add a note for everybody else who may potentially wander in to let them know. Did I spell it right? I think I did. Alright, cool. So we'll pin that at the top of chat. So we have sound alerts now. And I also have a couple of extra commands that I added due to some of your recommendations. You will find them down in the description. I added unlurk. There's lurk, which I had before, and I think I might have added one more. I don't know. It's down there though. But yes, we have sounds of the sound alert type, so that's fun. Don't know how loud that's gonna be. It seemed like I think I got it figured out, but you know, we'll figure it out. So with that aside, let's get started. We are going to scoot on over and continue with day 19. Once I find the right scene. There we go. Best of luck,
Rise and
Adit.
shine, explorer.
Lovely.
Today's the day we've been working towards.
Oh.
We're finally ready to ascend from the ocean depths and glide our spaceship back up to the watery
But
surface.
I thought we did that
I
already.
hope you're as thrilled as I am.
Doing what
The
I
past
can.
few weeks have been a test of your courage, determination, and your ability to think on your feet. And I must say, you've handled every challenge with intelligence and tenacity.
No.
You're proving to be a true explorer in every sense.
Nice
But remember,
try.
there is still much work to be done. Today, we will put everything we've learned to the ultimate test. All of
Okay.
your wiring, coding, and problem-solving skills are going to play a crucial part in our endeavor today. So, take a deep breath, clear your mind, and prepare yourself.
No.
Today, you're more than an explorer and an engineer. You're a brave starship commander, navigating tenaciously through the unknown. Strap
No.
in, explorer. It's going to be a thrilling ride. Are you ready?
Potentially.
It appears we're all set to make our careful ascent back up to the water surface. It's critical we do this gradually to prevent our shuttle from popping like a balloon under the change in pressure.
That would be poor.
Do you recall our trusty sidekick, the passive buzzer? I'd suggest we reintroduce him into our circuit as an additional safety measure. He'll be our alarm bell, warning us if we're ascending too quickly. Don't fret. I've got you covered with all the guidance you'll need, conveniently located in your mission resources.
Really
And guess
now?
what? They're ready for playback right now.
Okay.
Beginning playback.
Oh, we're good. We're good. You're good. I'm good. It's fine. I think I've got this. Or I get to show you in real time how poorly I don't got this. So interestingly enough, we're still toying with the idea of ascent. Now, even though we purposely made last time this circuit with the rotary knob and with the display, we're adding sound to this now. So let's take a look at our code, and then we'll cycle back. We'll see what's currently wired where, and then make appropriate adjustments. So we're going to take a quick peek here. Oh, interesting. They're having me reuse the keys from the previous day 17. I think I still have those written down here somewhere, I hope. If not, I might have to actually go pull that out of one of the older files. Let's see here. So we're doing that. Alert buzzer. Blink the depth gauge this many times for attention. Oh, that's blink counter. We're setting up the segments again. We're going to call interrupts. Should the number digit. Okay, all right, let's get everything wired, and then we'll take it from there. I'm just perusing through that to kind of see where we're at. I'm shocked. Day 19 looks an awful lot like day 18. All right, that's fine. Let's see what we got here. So let me grab us. We'll do a little scene switching action here. Maybe. There it is. Aha. All right, cool. All right, so first things first. Make myself a little room here. If I can get over here. Okay, so I purposely did not disconnect anything from last time because I've learned that we generally tend to reuse stuff in this space, and that's totally fine. Okay, good news, I also did not dispose of my sticky note that had the winning numbers on there for the decryption key. So it's 23, 353, and 1688 are the numbers that we need for this. I'm going to put this over at my desk so we can get into it. And then let's see what we got here. We've got our rotary knob from last time. Oh yeah, let me move this in a little closer here. There we go. All right, so we have our rotary knob that we could spin in either direction. There's no limit on this, by the way, so you could spin this all day, every day, and it'll just keep on cruising. And then we have our display. We also have, and let me take a look at our wiring to see if we were moving any of these items. I don't think we are. Looks like the display is hooked up to pins 5 and 6. And looking at this, that's pins 5 and 6. The rotary knob is an interrupt, and I remember from last time that it has to be pins 2 and 3, and it is. So all those items are exactly where they're supposed to be on this board. A brief callback to the last time that we did this, we found out that the rotary knob that we have in our example, when we spin it and we get input from this, that actually pauses the execution of the code. So once it does that and pauses the code, it reads how far that we spun the knob, and then it relays that back to the variable, and then the code picks up where it left off. The interrupt on this particular board is only available on pins 2 and 3. That means that you can technically have 2 different interrupts. Now, in the case of this particular device, that only means that we can have 1 because this requires 2 pins, the clock and the DT. The other 2 pins are ground and the positive 5 volts. They're the lower 2 wires on this device, which is fine. So, all right, so that means we just got to fish out the buzzer and get that wired in appropriately, which I now need to locate. All right, so we have our buzzer, this little guy, and we take a look at this. This is going to get hooked up to ground and pin number 10. So I'm gonna put our little friend here into our breadboard, standing up and down, so it's nice and easy to work with. I have that right here, and then I'm gonna grab us 2 wires. I'm going to use our brown to hook up the negative rail, which I have plugged into here, and then hook that into one of the available negative rails on this side. I don't have this side wired up, so I'm not going to use any of these. I don't see a reason to create a jump around this. It's really not needed. We're not adding anything too complicated here. And then I'm going to plug our far left into pin 10 on our developmental board. We're going to take our friend here, and we got 8, 9, 10. So wiring wise, that actually should be exactly where we need to be. Now, I didn't clear the code off of this from last time, so what I'm going to do is just plug it in. Give it a brief moment. We will see the previous code on here, and I can rotate this. We will see the display will in fact change my movements, right? We had it at, what is it, -40, -20, and then once we breached, we're done, right? So it looks like we're expanding on that, and in addition to displaying what we have on here, we're also going to add sound to this example using our buzzer. So we're going to get into the code now. Hey Byro, welcome on in. Yeah, so we've got that hooked up now. As long as I plugged everything in where it's supposed to go, this should be just rocking and rolling here. So let's do that. Okay. So we're going to see here that our we've seen comments at the top. So let's see what we're working with. It says, moving from day 18, let's get our ship moving towards the surface today. As we test our code from day 18, we noticed a few things that we can do to make our ascent even safer. The day 18 sketch allowed us to ascend faster than is safe, so let's limit the rate of ascension to a slow rate. In addition, we will add a buzzer to our circuit to give us an audible alert if our rise rate is faster than what is considered safe. Lastly, it turns out our safety stop depths are when we're 50% towards the surface and 75 of the way towards the surface. Let's make this sketch track our rise as a percentage of the way from our starting depth. All right, that seems reasonable. All right, so there is some changes to this, but just quickly, briefly looking at it, it didn't look like there was too many changes. So we're going to do a little bit of stuff here. So, okay, first things first. They did, interestingly enough, leave this in the code that requires the decryption keys before anything will work. So we're going to put these in here. And this is from day 17, these numbers. So that's going to be 23, 353, and 1688. I have those on the sticky note. And that was from a Shift 19 Shift Caesar register that allowed us to decrypt the code to get those numbers. If you're interested, the VOD is there if you're curious. So we got that over. And then let's see here. So it says the rotary encoder will be used to control our lander's depth underwater using the interrupts explained below, right? Since our hero board only supports interrupts on pins 2 and 3, we must use those pins for the rotary encoder inputs. So you can have technically 2 different interrupts, but with the rotary encoder, we need both of those pins must be on 2 and 3, which is the same as last time. So we're going to go ahead and bring this stuff over. So that declares pins 2 and 3. And then we also create a basic encoder object. So ours is, this is a basic object, right, that allows us to rotate and then read the encoder. Now we called ours depth underscore controller, or excuse me, depth underscore control. We then pass it which pins are the clock pins and which one are the depth control pins, which in this case is just 2 and 3. That maps our clock pin and DT pin. So the clock pin is to match up with the synchronized clock that's in our hero board. And then our DT pin is the actual data. So when you twist the knob in either direction, that's the information being passed from the encoder into the object. Okay. Then, after we've done that, we're then going to bring over some pin declarations for the display. We left that in the same place as last time. So it's going to be pins 5 and 6, doing the same kind of thing, declaring our clock pin and our DIO pin, which allows us to control all the individual segments to be able to change what's on the display. And then we're going to create another display object using the library, which actually I don't think I did the include on that. I have to go grab those. We're going to call it depth gauge because that's how deep we are. The object is going to be called a TM1637 display. Interestingly enough, they weren't terribly creative with that, but fair. Or excuse me, depth gauge is the name of that. There we go. That's the name of the display that we're using from that library, which let me go grab those. Those were right at the top here somewhere. Yeah, these. I didn't see them because they were partially grayed out. These must be at the top of the code for any of this to actually function. That's the Arduino class, which allows us to interact with the hero board. Our display class, which allows us to control the segments on the display. And the basic encoder class, which allows us to then read the values of the knob. If I were to call on any of these items to create any of these 3 objects, and I don't include the class that I'm trying to read it from, I'm going to get an error because it just doesn't exist, because it didn't include it. So we got those in here. And then we're also going to declare the pins for the buzzer. Now, we did hook up 2 wires, but there's only one that gets controlled by the Arduino, the ground and the actual buzzer itself. The buzzer control pin, or the positive, is going to be pin 10, and then the ground just goes to the grounding rail with all the other items that need to go to ground. There's no control on that. Let's see here. Next thing we're going to do is the blink counter. So this dictates when we blink the display how many blinks that we want to have, well, per blink. In this case, we're going to blink 3 times. So as in the current example, it would blink the word done 3 times. Boom, boom, boom. And that's from this value. But the nice thing about making a variable for this is that if we decide, hey, I want this to blink 10 times instead of 3, I could just update this one number, and anywhere else I use this variable in the code, it also gets updated. All right, so I copied things a little out of order. Okay, so then, yeah, all right, so then we need to do the segments. So what these are, this is us putting together the different things we want to display. So if I want the word done, right, then I need to turn on these segments on the several segment display. This is us hard coding which segments to turn on or off, and then all we have to do is just pass to the display the word done, and then it passes all of these segments we want turned on. Same thing for nope, same thing for hold. Make sure I save this as I go along. Okay, let's see what else we're bringing over here. So far, that's all the same stuff from last time, from us doing one of these. Okay, so our lander is currently this deep underwater, so this is what is initially displayed. Our initial depth is at -60, so we're 60 units underwater. You could choose miles, you can choose meters. They don't give me a unit. I'm 60 units underwater, so that's how deep down we are. And this is just a number that was chosen for the example. Anything that's positive would be above sea level. And then we're gonna set up some alerts. Now we can see here, ironically, we're gonna set up some alerts, and I have new sound alerts. I like that. There's sound alerts, by the way. Hopefully they work. You will find this in the channel point redeems. Because yes, we have some of those now. We've got 2 alerts that we're going to configure. Depth at 1 and then depth at 2. The first depth is going to be at or wait a minute. Alert depth 1 is at 50%. So first alert when we're... Oh, okay, I understand now. I read these numbers backwards. I'm like, what? So the first alert is when we're halfway to the surface level. And then again, when we get within 75% of the way, which is 25% of the original depth. That's what threw me for a second, because I'm like, that should be 0.75 if we're trying to figure out 75%, but we're starting from a negative number, so it has to be the reverse for the percentage. So it has to be 25, which actually makes sense. When you're working with negative numbers from the start, you have to remember that if you're going to grab a percentage, that's actually backwards, which is a little funky. And then looks like I brought over... I actually brought over the whole void setup when I did that. So I'm just going to nuke the copy I accidentally made. And we are going to configure in the void setup the buzzer on pin 10 is an output, because we're going to make some sound with it. We're also going to use the serial monitor so we can see in the little window down here that I have to turn on. Let me do that. This area down here, what is going on with the board. We've used the serial monitor before. It allows us to see in real time the values that are rolling around on the board. We're then going to delay for 1,000 milliseconds, which gives us just enough time for everything to get all ready to go. That delay there is just to give the serial monitor a possibility to get ready between the board and Windows. Because if you try to start reading serial data before the port is opened, you won't get anywhere, you'll get an error. So they hard-coded a delay in there, which makes sense. Okay, so we're not done with the void setup. We have a little bit more we need to do. So I'm going to bring the rest of this over. I'm going to verify this real quick because I may have accidentally... Oh, that's fine. I didn't declare that because I haven't gotten to it yet. All right, ignore that error at the bottom of the screen. We'll get back to that. Okay, so we're going to set our brightness on our display, which 7 is maximum brightness, from 0 to 7. I don't know if 0 is even visible, ironically. I think we're going to toy with that, and we'll see after we get it all together what it actually looks like. And then... So keys are valid is the function I haven't declared yet. I have to copy that. That's why we're seeing the red. So this is the thing that's going to either show our initial depth and take us into the loop, or it's going to throw an error and keep us hostage here until the proper decryption keys are put into the code. Now I've entered those already. Those are the 3 numbers that I put in here up above. These 3 right here. It does a little bit of security through obscurity. I'm sure there's a decent enough way to reverse engineer this check, but we have it, what we need. So with that action involved, we've got what appears to be the remainder of our void setup, which I do recall us doing this. Again, I still haven't declared that other thing, but that's okay. Yeah, keys are valid is not. Update encoder was not declared. That's totally fine. I have to declare them. So when a declaration's missing for code you're going to call on, it'll throw an error saying it can't find the code you're talking about. So the error could be ignored. As a matter of fact, I could make it go away. Okay, so we have 2 interrupts that we need to have action here, right? We need an interrupt on pins 2 and 3. So we're actually going to declare interrupts on both of them. So we're going to declare it on the clock pin and then again on the DT pin. We then, when the interrupt pauses the code, need to tell it what do we want to do. The variable called update encoder is where we're going to store the change. And you can see here that what we're doing is the change, right? The macro that we're going to run. Which I'm wondering if I hover over this. Right, so that's the definition. Yeah, attach, interrupt is the pin, which is a number. And then update encoder is the function it runs. A void function with no return, and then what it does in int mode. All right, that's fine. The yeah. We have one more item that lives outside of the loop, and that's the delay. So the delay in milliseconds between the loop executions. Now remember, when we rotate the little dial, it's going to, we did a thing. We did a thing! Dragonus! Hello! Thank you for the raid. Oh god. Oh, we're haunted now. Yeah. Yep, my code is haunted. You are correct. I have sound alerts now. I also have a couple of other commands that exist in the description, which I'm working on it.
Can I get a glass of water?
Oh, I forgot that's what I said for the hydrant. Hi everyone. Welcome to this madness. Oh god.
Save me!
Save my work. You're not wrong. Let me do that. Dragonist, tell me, what were you guys doing? I'm very curious as to what you were up to. I'm here melting my brain with everybody else. Ooh. Okay. Playing a game. I'm imagining that's an abbreviation for something. I am really bad with abbreviations. Oh, Animal Crossing. Roger. A set. Join the club. We got hot takes. They're so toasty. And there's code. And there's melting. But yes, for those of you who don't know me, I am TechHead41. I play retro games, and I also do stuff like this, where we talk about technology. This evening, we are continuing our adventure in the 30 Days Lost in Space franchise. We're trying to get our lander off the bottom of the seafloor, but we're trying to do it in a safe fashion. If we go too fast, our ship will explode like a balloon. It'll go pop. And then there's bits and pieces of us everywhere, which is less than ideal. So what we're working on getting our spaceship back together with some appropriate hardware that won't only just display our depth and give us control on how fast we go up or down, but also a buzzer to indicate audibly, hey, you might explode if you don't slow down. So that's what we're working on. Working getting the code into this. And if I do a little show and tell, we have our display right here showing that we're at a depth of -60. And we also have our little knob will spin. And then we're working on getting the code together for the buzzer that we have right there. Yeah, that's what we're up to. So far, we've gotten the initial setup of all of our code in here, and now we're just about to start working on a loop. We're about to go loopy. Let's see how much of this I want to bring over in chunks. This one's kind of long. So let's grab this a few chunks at a time, shall we? Okay, so we have to have, of course, an initial depth, and that's based on the previous depth, which I don't think we actually declared anywhere. But that makes sense, because obviously if we proceed to go up or down in depth, we need to update our depth based on our initial depth if we don't have anything. So it says here that the depth from the previous loop initializes to our initial depth first time through the loop. When changed, it retains its value between loop executions, which makes reasonable sense. So we do that there. And then if the depth control dot get change, so the control is the knob, right? That's the thing we can actually rotate that we have on the bench here. We then call upon to set our current depth equal to our initial depth plus the change that was captured from spinning the dial. Now the dial allows us to spin clockwise and counterclockwise, which will either add and cause us to go up, or subtract and cause us to go down. Now, the spaceship can only go so deep before we're sitting on the sea floor. We're currently there right now. We're at -60. They didn't give me a unit, so -60 units underwater, and we can't go lower than that because we're sitting on the sea floor, right? So our code's going to accommodate for that. Now we are baking some safety functions into this so that we don't go too fast and go pop. That would be what we consider a bad idea. Did I miss a... I don't think I did. So I thought I missed a curly brace, but I don't think I did. Oh, it's right there. Yeah, I want to be below that. Because that's the one for right there. That must mean that I accidentally nixed the ending of the loop. Which I must have boo-booed. And if I actually take a look now at our loop here, that's the setup. And there is our... Nope. I was right the first time. Yeah, I am. Okay. Continuing onwards. We have our depth, and then we need a variable to calculate our percentage of ascent. So we have a variable that is going to be a byte in size. A byte can hold anywhere between 0 and 255. If the number is bigger than that, or smaller than that, we need to use a different type. This type of a byte, think of it like a Tupperware container. If I try to fit an entire French bread into a tiny little Tupperware container that's the size of a piece of bread, like sandwich bread, that's not going to really fit, because a French loaf is really, really big, right? And sandwich bread is really, really small. Well, the same thing happens with variable declarations. A byte can only hold so much bread. And if the bread's too big, it buffer overflows, and then you have a problem with your code. So, to do a little bit of math, we're going to take 100%, subtract from that the current depth times 100 to turn it into a percentage, and then divide that, to turn that into a decimal, and then divide that by the initial depth. So initial depth starts at -60, and divide that by where we are times 100, and then subtracting that from 100 equates to the appropriate math to get us a percentage of where we are in the world. That's really just the same procedure for figuring out a percentage of a number, but instead of hard coding in here all the numbers, we use these things called variables, which allows the code to figure it out on our behalf. And then this is the part where we're going to add some sound to the code. So it says rising too quickly could stress the hull of our lander. Because of this, we want to play an alert if the lander is instructed to rise faster than 1 meter every time through our loop. So integer rise rate is going to be equal to the current depth minus the previous depth. That tells us how far we've gone. And then if the rise rate is greater than 1, then we're going to buzz. We're going to turn the pin on, and we're going to delay for 200 milliseconds. Now that's the same amount of time as the loop delay on how many times we go loopy-loop through the code. We pause for 200 milliseconds. And we're doing the same thing here. We're just reusing the same thing. And we're going to hear a buzz, which I would think that's going to actually buzz probably about every time, because 1 is a pretty low number there. Okay. So it says we cannot go deeper than the initial sea floor. So this is the code that is going to prevent us from going lower than -60 because we're sitting on the ground. You can't go below the ground. You are not Gary's Mod no clipping through the floor. That's not happening here. So we have this little nugget of code that basically says if we try to go lower than the initial depth, to just reset it. You're not going to cause anything lower to happen. It bottoms out the code. It just resets the encoder. So if you keep spinning it in the negative direction or counterclockwise, it just resets it. It doesn't actually take the value and do anything with it. Okay. So then, now that we've gathered some information, we need to show on the depth gauge where we currently are. So we're going to show the number of our current depth by just passing it to the function, and then the library goes, oh, I know how to do that. I know how to show the number in decimal. And then bloop, up on our little display that we have on the bench is where the number is going to appear. Then we have some notes here. It says, since the basic encoder can be clicked multiple times per loop via the interrupts, we track when counter has passed a milestone, this time through the loop. We do by testing where the previous counter was less than the milestone's current counter or greater or equal to. So if we go above 50% or above 75%, because those are the two levels that we decided to choose based on the example, then we're going to do something about it. And let's see what we're actually going to do about it. All right, so it says if we crossed our first alert level, then flash hold on the display. So that's going to take our first alert level was at 50%, which we could see here by looking at the hover note. And we're going to blink that action, right? If we then go over 75%, which to get that is based on 25% of the initial depth, which is 0.25, we're then going to blink that number in our face using the blink depth function that we're going to write. Okay, so it says, we have reached the surface, blink done on our depth gauge, and play a happy completion tone. That's what this block is for. So let's see how that's set up. So it says, if the current depth is equal to or greater than the surface depth, which would be 0, because we're now back to the top, right? So 0 or greater means that we are now above water, or we're at the top of the water at least. We're going to play a ta-da tune on the buzzer. So we're going to play the first tune, delay for 200 milliseconds, which is what the loop delay is for all of these. We're going to pause for that amount of time, and then we're going to play the lower tone. So the sound that we're going to make is this number, 440, and then we're going to pause and then play 600. So that's going to be like a doo-doo or doo-doo. I don't know, one or the other. We'll see here in a minute. It's going to change tones. It's going to go from either low to high, high to low. And then from there, we're going to blink based on our blink counter 3 times, 0, 1, and 2 through our loop. We're going to clear the depth gauge, pause for 300 milliseconds, and then display the word done, and then pause again. So that's actually going to blink the word done 3 times. Boop, boop, boop. Then that's iteration 0, 1, and 2. 3 is when we break out. But it still gets 3 segments of the loop. Then from here, we then take our previous depth, excuse me, and then set equal to our current depth. And then the loop is going to pause and then continue again. Now, earlier I had mentioned that we had to declare the code that reads our keys to figure out if we're even going to run any of this. That's when this is going to happen. So as I had mentioned, that in day 17, we did have in our code here this obscurified thing, right? If the keys are valid based on the 3 numbers I provided at the top, based on this gibberish, it's going to return whatever it needs to proceed. Like I said, for those that do cryptography for a living, I'm sure someone could figure this out. But honestly, this was clearly written to be obscurified and not easy to understand. I'm sure that if given the time and opportunity to like work through this, it's probably not that hard to figure out what this does to be able to defeat it or bypass it. I mean, if I really wanted to defeat it, I could have just deleted it and just told the code to start running without even checking for the keys. But obviously it's here. I want to point this out because it's here. And it would be easy enough to ignore it if I had trouble with it, but just know that this isn't any more secure than putting a plain text password in place. It's going to take a little time to figure out if one needed to get around it, but it's doable. But nor here nor there. Okay. All right, we have the last little bit of code to look at here. And I know I missed a semicolon in there somewhere, or not a semicolon, a brace in here somewhere. So what I'm going to do is I'm just going to bring over the rest of this, so I don't have to spend the next 15 minutes trying to hunt down a brace I forgot to copy. And we're going to cover the rest. So we have the blink depth function that we have here. Any code that is written with void at the beginning of it as a function, it's a block of code. You could just call it multiple times. So what does that mean? I'm glad you find it fascinating. There's a lot of moving pieces here. A void function is a set of tasks that you can call on as many times as you want to, right? So if I said blink the depth, right? Well, I need to know what depth we're currently at, right? So I need to accept an integer of how deep we are, right? And then based on that, I then go into this loop, which runs 3 times because our blink counter is set to 3. The I, which is just an incrementer, which is why it's an I, is set to 0. And that means we're going to cycle through 3 times. 0, 1, and 2. At 3, we break out, so it doesn't run that 3rd time. Based on 3, which should technically be 4 because we started at 0. That part's still confusing. Loops start at 0. 0 is the beginning of an array. A list of things. If I'm storing 4 things, I'm storing it in objects 0, 1, and 2. And 3, if there's 4 of them. So for loops that I want to run 3 times, it's 0, 1, and 2. A little confusing, I know. Everybody's used to starting counts at 1. Why did we do this to ourselves? I don't know. That's coding in a nutshell. But I could call on the same little block of code, which will then say, we'll call on our hold that we wrote up above. So let me scoot back up to that for a second. Let me show you where that's relevant, right? So I'm telling it to set hold and display that. So let me scoot back up here to where that lives. These are our words, done, nope, and hold, right? So right here, the code doesn't know how to spell a word, right? We have to tell the compiler what hold means, right? We know that if we turn on these segments that we get an H, and if we turn on these segments we get an O, so on and so forth for the L and the D, right? Because we're assigning meaning to these little segments that are on the display, right? Let me show you, right? So on our display, we're displaying -60, are all these little individual segments, right? And what we're doing is we're turning on and off all these little chunks of the display. When they're all turned off, they look like an 8, right? That's all of the segments off. But if I illuminate all the outer rings and don't turn on the center, well, then what does that look like? It looks like a 0, right? The code doesn't know nor care what it's displaying. We assign the meaning, and then when we see a word done, well, we assume whatever we were working on has completed itself. The code doesn't know or care. That meaning is for us. So you have to be a little careful when you're assigning meaning to things in your code, because the compiler doesn't care what you're doing. Not that that's a problem, but if you do run into an issue where something's not exactly working as you intended, you need to remember that what you're doing is based on your logic. And if the compiler doesn't run through the same logic that you have in your head, well, then there's probably a logical error in there somewhere. Good example of that. If you had to run a race, right? And you start at 0 and you have 10 miles you're going to run, right? Well, then that means that when you are done running the race, you are at 100% completion. You can run as much as you want, but you've completed the task, right? So you can never be higher than 100% when the race is anywhere between 0 and 10, right? Because you ran the distance. So if you set yourself up where you wanted something to happen at 110%, well, then guess what? That's never going to run, right? If you want someone to run out and dump a big pail of water over the winner's head if they complete 110% of the race, mathematically, that's never going to actually happen. Because, mathematically speaking, a percentage of completing a task is only going to be somewhere between 0 and 100. If you've exceeded over 100, well, then you have parameters in the thing you are doing to go beyond that. But in the concept, right, the mental concept of running a race, that's not a thing. Yes, we're going to dump the energy liquid on the toaster. Okay, yes, that's 100% how this is going to work out. So with that, we're assigning the meaning, right? And you can't call on something that is outside of your capabilities, right? Because that's a logical error. It still runs, but it'll never be true. So when we write code, we have to be careful when we assign meaning, that we don't accidentally assign meaning to something that can't happen. That's why when you're troubleshooting your code, you want to take the time to go through all the different scenarios. Good chance in this, I need to enter the wrong key, which would prevent me from running the code. That tests the beginning of the code. I want to rotate the knob below -60, which should send me into the ground, right? This is testing. This is something you should do when you write your code. This is also something when people make games also need to do. They need to test things, which is why usually developers hire testers. Or they ask a bunch of people like, hey, could you test my thing and see? I want you to try really hard to break my game, okay? In like the best fashion possible. Because understand something, games look a lot like this sometimes. There's coding involved, right? And if you accidentally choose a number that does something that you didn't anticipate, well, that's what your testers are for, to find out how screwed you've just made yourself and what you need to do to fix the problem. Because when you're running code in a compiler, you may set yourself up for success or failure. Kind of depends on what you're trying to accomplish. Let me get back to the example. It's crazy. It's also nuts. So yes, that's a big old nope right there, right? Okay. Excuse me. And then we have one more void function that's here at the bottom. And that is the service for the depth control, right? So we have an interrupt, an ISR, which lets the encoder library handle when we rotate the knob on the encoder, which changes the numbers, which pauses our code wherever we are. After it's done that, the code picks up where it left off, and then the loop just at some point reads that information and then runs with it. So now that we have all this in here, we're going to verify our code. So I think I already took care of that part. Yes. Okay, we're now going to upload our code. Haha. Oh, well, would you look at that? I mistyped the keys. Invalid keys. Please enter the 3 numeric keys from day 17 in order in the keys array at the start of the sketch. Okay, I'm game. What did I put up here? Oh, wait, I know what I did. I copied over the entirety of the code, which means these are all zeros again. Hold up a minute. I need to put the numbers back in. Look at that. I tested that without even trying. So this is supposed to be 23... 353. Yes, I am a goober. I'm aware. And 1688. Okay, beauteous. All right, so I'm going to re-verify that to make sure I didn't screw anything up. And I'm going to upload it now. I also didn't I didn't clear the serial monitor. Let me do it. Let me do that again. Okay, cool. So we got nothing in the serial monitor, right? So behind my floofy head here, there's nothing in this area, right? So if we take a look at our display now, we're gonna see some action here. And if I hooked everything up correctly, we should hear some things too. All right, let me get us a little in frame here. Okay, so our display right now is at -60. And then our rotary knob is going to change our depth. And then our buzzer that's down here in the lower left of frame is going to hopefully make sound if I plugged everything in correctly. So the first thing I want to do is rotate this counterclockwise. And as we can see, the code is working correctly. I am not going lower than my lowest depth. We are at sea level. We can't get lower than the ground. We're at the ground. So now, when I start rotating in the other direction, we're going to start raising. I'm not spinning this terribly fast, right? And we're rising and we're rising. And if I go the other way, oh, now we're going to start sinking again, right? So the numbers are changing. Now I'm going to try to go fast because it did say that supposedly we're going to hit a hold if we go too fast. Ooh, check that out. It got mad. Let me get my microphone close to this so you can hear this. Look at that. It's actually blinking hold. You're mad. Right, so that's to indicate we're going to have a bad time. I could resync the ship. So that actually indicates I did plug everything in where it was actually supposed to go. Because I was supposed to plug this in on pin 10, and I did, because we heard stuff. I am notorious for accidentally plugging things in either the wrong place or backwards, because these are really small numbers. But that's okay. That's why we test, to make sure that things are plugged in where they're supposed to go. So, yes, if I spin this really fast, I should upset it. Yep, hold, it's mad. Or if we just take a nice, chill ascent here. Actually, let me get this back down and go quickly, right? Because it did say, we did have the code in here about going over half, right? So -30 should be the halfway point. So let me spin this a little slower here. So hold was at -30, right? And then that's halfway, so then 75% will be the other hold. There it is. at negative 15%, we're 75% of the way to the surface. That's what the other hold was for. Now, I didn't necessarily say how long we're supposed to sit at this depth for, but the important part is not to explode like a balloon. Because the hole kind of needs to stay in shape on the ship so that we all don't go, back to the seafloor in a rapid fashion. That's funny, if I spin this too fast, it gets mad. And there you go. Because we did set the code that if it's a rise faster than 1 meter of depth change in the positive direction at a time to make the buzzer go off so that we don't ascend too fast. Because the code didn't have that before. This actually then indicated that we're not only doing it, but we're doing it safely. Because the idea of popping like a balloon in the middle of the ocean kind of seems less than ideal. And that's understandable. But, oh yeah, speaking of that, hang on, let me get us back to being broken where I didn't have the key set. I actually forgot to show you that we got Nope that would have appeared. Haunted. Indeed. Haunted code indeed. Let me get back to the sketch here. Let me put one of these numbers in incorrectly. Because, as I had mentioned before, we did have to put a key in here. Right? And what that's going to do is tell me nope. Because I have the wrong decryption key in the code. Which means no. Probably please go away. This is only lit up to look like this because we hard-coded which segments to turn on. Right? So we turned on this lower one, the center one, the other leg, and then the outer side to make a 0 that looks like an O, right? For a P, we have all the segments but the bottom right-hand corner. And the same thing for the E. We just kind of spelled it out and turned off a couple of the segments, right? By only turning on the ones we needed across all the display. Now, this display does in fact actually have a colon in the center. I don't have it turned on though, because we're spelling a couple of pretty basic words here. And that's totally fine. And then, if I switch that back, re-upload the code, we're going to see some magic here where that nope is going to disappear. Now, something that you just noticed there briefly when the code was re-uploading is that we had a couple of segments stay turned on here, and then negative 60 reappeared, so now we can again officially use the example once more. It's Anki. Nope. That's funny. I got it actually above. I can actually keep making it do that. We're going. That's actually pretty funny. I mean, we're now 40 meters above the surface of the water. Yeah, we're a spaceship that's now very much above land. Bugger, I lost my train of thought. Well, we're above land. That's the point. Wah. Huzzah! Yeah, so that in a nutshell really makes up day 19, which is surprising. Looks like, let's see what else we got here. So we're going to have some additional stuff going on here. Looks like we're going to have a creative day for day 20. And then we've got only a couple of days left. Day 30 is the ending of this. So we're certainly going to keep trucking along here. Let me see what time it is. It is time. Indeed it is.